All right, here we are for the next free response problem in the back of the momentum packet. This one is from 1994. That's right, the year after the previous one. And it's a similar looking problem. They used to release the exams, like they would release one every, well, it was supposed to be, I think, a 3-year cycle, and they pushed it to 5. But anyway, and so like for that 3-year period, like it was like kept secret, and so they would have problems that were kind of similar to each other, and then like every few years, then they would release them all, and then have to come up with brand new problems for the next few years. So you kind of ended up getting kind of similar problems for a few years in a row. Not anymore. Anyway, get back to this. A 2-kilogram block and an 8-kilogram block were both attached to an ideal spring, for which the spring constant is 200 newtons per meter. Both are initially at rest on a horizontal frictionless surface as shown. Again, just looking at the picture, you see, I can see, look, just look at the picture. This ball of clay comes flying in. You say, oh, it's going to collide there, right? So there's going to be like a collision, and then look, it's going to like crush that spring. This is a removable stop there. So you kind of wedged into the ground, so it's not going to go anywhere. You can bet that eventually they're going to remove that stop for some later part of the problem. Or you can kind of predict a little bit what's going to go on. And you're thinking, okay, collision is probably going to be conservation of momentum. A spring, crush, and expand, probably going to be an energy thing. Anyway, moving on. In an initial experiment, a 100-gram, 0.1 kilogram ball of clay is thrown at the block. The clay is moving horizontally with a speed v. When it hits and sticks to the block, the 8-kilogram block is held still by a removable stop. As a result, the spring crushes a distance of 0.4 meters. Calculate the energy stored in the spring at maximum compression. You say, well, gosh, if with the spring constant, I know the energy stored in a Hooke's law spring is 1/2 kx squared, and I know, okay, that energy stored when it's at max compression, that everything is going to be still again, right? When this hits, it speeds this up in the collision, and then they're moving, and then it comes to a stop, and then it would spring back. So all the energy is in the spring at that point. Anyways, the point is, I can find the energy. They're just all I need is 1/2 kx squared. I know the k. I know the crush distance. I can go. So here we go. I'm just going to say for part A, I'm going to use the energy stored in the spring. I know that formula is 1/2 kx squared, and if for some reason I don't remember that, I can look on the AP formula sheet because I will have it. All right, and the energy stored in a spring, he says 1/2. The spring constant they told us was 200. The crush distance they told us was a whopping 0.4 meters. That's 40 centimeters. That's a chunk. Anyway, so doing that out, you say half of 200 is 100. 100 times 0.4 will be 40 joules. All right, so that's my energy in that spring. All right, let's double check our work, shall we? All right, and find that I screwed that up. You know how I screwed that up? I didn't square that 0.4, did I? Dave. Okay, anyway, if I go ahead and multiply this by 0.4, you say that's like multiplying by 4 and dividing by 10. 4 times 40 is 160, divided by 10 be 16. Wow, that's not ideal. Okay, so anyway, if I go ahead and I take a look at the scoring guide for this one, all right, because see how they assign their points, and you say, sure enough, for using the formula for energy stored in a spring, 1/2 kx squared, bink. Substituting in the correct values, 200.4 squared, bink. And then for my final answer, including units, 16 joules, bink. Hey, that's 3 points. Done. All right, that's the first part. All right, continuing on. Part B. Calculate the speed of the clay ball and the 2-kilogram block immediately after the clay sticks to the block, but before the spring crushes far. I know, technically, while this was hitting and squishing, this would start moving and it would start crushing the spring. We're just going to assume it's kind of a immediate sort of collision. Assume it hasn't crushed significantly yet. So I'm not going to worry about the spring applying a force against the block yet. All right, because the force is 0 before it gets crushed. I'm just going to use a conservation of momentum thing here, right? So we're saying for conservation of momentum, we know that the base momentum formula looks like this. We're saying we're looking at momentum in the horizontal axis. You say, what horizontal forces are there if I treat the clay and the block as one system? If the only outside things touching it are the tabletop and the spring, we're going to assume the spring hasn't crushed significantly, so the force from the spring is negligible. And the floor, they said, was frictionless. So really, there's no horizontal forces here on that combined system. There's forces between the clay and the block, but we don't care about those. They're inside. So the external force in the x-axis and the horizontal axis is 0. So that will just drop out, right? Which means delta P is 0, which means the initial equals the final. I don't know why I switched colors there. So then we want to find the speed immediately after it sticks, but before it springs. So beforehand, I have the clay. So it'd be like mass of the clay, the velocity of the clay has to equal the momentum afterwards, which will be, it's going to hit and stick, right? And so then they're going to move together. So it'll be perfectly inelastic collision. The two masses, mass of the clay plus the mass of, I don't know, the small block times that V after the collision, right? And so you see, I can find that V after the collision because I know all the rest of these values. The clay ball is 0.1 kilogram. Its initial velocity, they tell you, is rut-row. Okay, I see. They didn't tell me that. That's just V. Aha, okay, I see what I'm going to have to do. Okay, mass of clay plus mass of the spring. You're saying, hey, that's going to be 0.1 plus the mass of the small block, which is 2. And then there's this V final. That's the speed after the collision. You're like, oh, what? I don't know that. How fast is it moving after the collision? So you notice that in the previous part, they had you solve for the energy stored in the spring. So what I'm going to do is I'm going to say, well, where did that energy come from? It came from the kinetic energy the clay and the block had after the collision. And that kinetic energy gets converted into the energy in the springs. It crushes the spring. So that's it. So I can find that by doing an energy calculation. I'm going to look at it from when, right after the collision, to when the spring is fully crushed. Does that make sense? So we're going from right after collision to spring fully crushed. I'm going to make my system be clay and the small block and the spring. I'm going to throw the spring in right away. I know I'm going to want to do that because look, I have U spring there. So if I do that, I'm going to have sigma W is delta K plus delta U spring. Because I made the spring part of the system, I can have a delta U spring. What horizontal forces are acting as we go from there to there? Nothing now, right? Nothing. So I've got 0 is final kinetic energy minus initial kinetic energy plus U spring final minus U spring initial. Right? At the start, we are cruising along. Sorry, let's do this. At the end, right, the block is going to get stopped completely by the spring. So this K final will be 0. But K initial is 1/2 the mass of the clay plus mass of the small block times the speed after the collision squared, right? 1/2 kx squared, 1/2 mv squared. Sheesh. The energy of the spring at the end, hey, that's 16 joules. I ran out of room. U spring final. I don't need to break this down to 1/2 kx squared because I already solved for it there. And then minus the initial with the start, the spring wasn't crushed yet. So this is it. There's just these two terms. Moving along here, I can move this 1/2 mv squared to the other side. Mass of spring plus mass of the clay times the velocity of the clay. I'm sorry, the final velocity squared equals that energy in the spring. Okay, which I know is 16. I can solve for this V final, move that over there. U spring final minus 1/2, I'm sorry, divided by 1/2 mass of the spring plus mass of the clay. Yeah. Okay. You know, they gave me values. I'm going to go ahead and stick my numbers in right now, just to make my life easier. I mean, I could take the root of this, right, and then stick it in here where it says V final and solve for VC. I'm just going to go ahead and get the value now and make it a little bit easier. So I'm going to take the root of 16 over 1/2 of 2.1. That's the mass of the spring and the clay together. Okay, that's my V final. Let's get a decimal approximation. 16 divided by 0.5 times 2.1. Now take the square root of that. So I get that V final to be 3.9 meters per second. And yeah, I'm rounding a little bit, but that's fine because it's 3.903. I can round that 3.9. Okay, now I'm going to go ahead. I'm going to substitute that in here. Now I can find that VC. I'm going to move that 0.1 to the bottom here. So I'll have that 2.1 times that V final, that 3.9. I'm dividing by that 0.1. All right, punch that in the calculator. My answer there times 2.1 divided by 0.1. So what I'm getting here is that speed of the clay before it hits is really honking fast. I got 81.975. That's like 81.98, or 81.98. I can probably round that to 82, don't you think? Meters per second. They're giving me like 1 sig fig in this problem. So, all right, there we go. All right. Hey, let's check on the scoring and see how I did. Here we go. Looking at part B. Yeah. Hey, I just solved for the speed of the clay before it hits. That's not what they wanted me to find, is it? They just wanted me to find the speed of the clay in the block after. Then they want me to find the initial speed of V of the clay. I just solved for part C. I'm getting, look at that, predicting what they were going to ask. They want to actually, oh my gosh. Oh, well, here. Well, that's it. I just did B and C together. The speed of them after the collision is that 3.9, right? Yes. Okay, and that's what it is. Okay. So here. So I accidentally did part B and C together. So let me just adjust this. Hey, look, this is part B, and look, this is going to be my answer for part C. Okay, here we go. Sorry. So the scoring. Part B, they say for using conservation of energy, you get a point. Hey, look. For, let's see here, kinetic energy of ball block combination is the energy stored in the spring. For correct expression for the kinetic energy is just equal to potential energy. Hey, that's what I did here. The kinetic energy is equal to potential energy. And then the correct answer, 3.9. Okay, so that's 3 points for part B. Part C, they say applying conservation of momentum, right, which I did here, saying the initial equals the final. For a correct expression for momentum, MV is MV, where big M is the combination of the two. In their answer, they call that big M. I just wrote it out. That's it. Okay, and then the final answer, 81.9. Hey, I feel pretty good about that. So that's 3 points there. Okay, what I would point out is a couple things. I got my notation. I did something bad, and that is I had to come up with, because I was looking at this next part, I was kind of looking ahead, and I went ahead and I invented some variable names here, right? I called this clay, and I called this, small block M sub S for its mass, and I called, this M sub C for the clay, right? You know what I mean? But later on, like they assign some things. For example, the clay is moving horizontally with speed V when it hits and sticks. So that speed for the clay at the start, I shouldn't have called it VC. No. Use their variable names. That should have just been V. Okay? Shame on me. Okay? Okay. Secondly, yeah, that's it. Okay, they didn't give me any other names, so the fact that I called this VF is fine. All right, good enough. Okay, but I should not have called that anything, but I should use their variable. Okay, so that's speed of the clay. All right, moving on with it. Okay, that's part A, B, and C. Okay, now they say, in a second experiment, an identical ball of clay is thrown at another identical 2-kilogram block. But this time, that removal stop has been removed so that this 8-kilogram block is free to move. So, state whether the maximum compression of the spring will be greater, equal to, or less than the 0.4 meters it did in the first experiment. So first experiment, this clay ball comes in, smashes this, crush, 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 crush. You got to know that while this is crushing, it's pushing against this block. That spring is pushing on the other side against that block, but it's connected to the stop, so it's the stop's in the way, so it can't actually go anywhere. Well, now, and so you end up all that energy that you had of this moving, the clay and the block moving after the collision, all that energy gets converted into crushing the spring. Well, now that's removed. When this hits and it starts squishing the spring's going to start pushing on this guy, and he'll start to accelerate. And so the big block here is going to gain some kinetic energy. So not all of the energy is going to go into crushing the spring. Some of it goes into moving this block, right? And so that spring will not crush as far. All right, so state when the maximum compression be greater than, less than, or equal, and then explain. So for part D, I'm not going to be able to squeeze this whole on this page, am I? Well, maybe I will. Probably not. Part D, I'm going to say, first of all, that max compression will be less than in the first experiment. Okay, make it clear which one you're saying is going to be less. All right, it's less than in the first experiment. I have to explain because in the second experiment, all right, I probably shouldn't abbreviate experiment, but that's okay. In the second experiment, see, this is why it'd be great if they gave these blocks names. It'd be easier to talk about them. The 8-kilogram block is free to move. So some of the original kinetic energy of the clay ball 2-kilogram block system will transfer to the 8-kilogram block kinetic energy gain. Instead of contributing to the energy in the spring. Therefore, the spring won't have energy to compress as far in the second experiment. All right, there we go. Good enough. Let's see here. I suppose I'm supposed to check the key. Let's see what they said they wanted for part D. For part D, they said, indicating the maximum compression will be less. Hooray! We answered their question. We get a point for that. For a correct explanation referring to the motion of the blocks or their kinetic energy, here's some examples. The 0.8 kilogram block will begin to move before the spring can compress as much due to the force the spring exerts on it. Okay, that's true. The kinetic energy of the center of mass of the system in this case is non-zero, right? At the start, the stuff's moving. Okay, so the center of mass is moving. Oh yeah, and at the end, there's no friction, and I don't have the stop there to push. So actually, the system starts moving. The clay ball's moving, right? A combined system of everything now. there's no horizontal force. If I consider the clay ball and this mass and the spring and this mass as one big system, that stop's not there anymore. There's nothing to push sideways on it because it's frictionless. So the total momentum before has equal to total momentum after. Okay, so that's interesting. So the center mass has to keep moving along. And so I know that the kinetic energy of the center mass is going to be non-zero. So some of the initial energy must remain as kinetic. So in the first case, because of the stop there, all of the energy went into the spring. And so there's no kinetic left. The center mass wasn't moving anymore because of that outside force from the stop. But now that's not there. So yeah, so it's got to remain, some of the energy has to remain as kinetic. Less energy is available as potential energy, so spring compression is less. Okay, I think we got it. Okay, I think we can agree that our explanation was suitable because some of the energy goes into the motion of the big block. Yep. Okay, so that's 2 points for that part. Okay, hey, there's one part left, and that part. Part E. State the principle or principles that can be used to calculate the velocity of the 8-kilogram block at the instant the spring regains its original length. So it's going to hit. So clay ball comes in, hits the one block, right? The spring starts to crush, but also push the big block, so that starts to slide, right? And then the spring would kind of crush down and kind of uncrush and crush and uncrush while the whole system keeps moving to the right, as it crushes and uncrushes and wiggles and jiggles back and forth. That's what's going to be happening. Can we figure out how fast the 8-kilogram block will be going the instant the spring regains its original length? If I were doing this, I would be using probably two things, right? I'd be using conservation of momentum because that center mass has to keep going at constant speed. And I'd be using conservation of energy, saying, oh, when the spring's back at its original length, there'd be no energy left in the spring. It would all be in the kinetic energy of the block and clay and this 8-kilogram block, right? You know what I mean? The kinetic energy of those guys. So I could do like a combination of those to make sure momentum is being conserved and energy being conserved. And that's what I would do. And it says, write the appropriate equation and show the numerical substitutions do not solve for the velocity. Okay. So perhaps I would do something like this for part E. I'd be doing a conservation of momentum. And so I'd be saying, I'd be saying the initial momentum equals the final momentum. And so I'm going to say that I would have, well, I know the total momentum of the system at the start is just the momentum of that ball of clay, right? So that would just be the mass of the clay times that initial velocity. The plus 0. There's nothing else moving yet, right? At the end, I'm looking at when those guys are, the spring is back to its original length. Now, these are tied together, right? But they're going different speeds as they wiggle and jiggle, yeah? Yeah. So I can't say too much about it. But let's just say it's going to be the momentum of all the parts of that system. So it'd be the mass of the clay plus the mass of the small block times the velocity of the clay and small block afterwards. That's really nasty. I guess I'm going to call it small block at the end because it's actually both of them together. Plus the momentum of the big block times the velocity of the big block afterwards, right? Okay. We are trying to find the velocity of the VB. This is the thing we're trying to find, okay? So there's one equation that has it, but it has another unknown, right? You see that? So there's two unknowns. I know all the masses. I know the initial speed of the clay ball. We solved for it before. Okay, so that's one equation. The other equation is going to be conservation of energy. And so I'm going to say at the start, now I'm not going to go, well, this equation is true, and I can use it because I know those values. I don't want to do a conservation of energy from before this guy hits to after, to that point that we're looking at where they're scrunching and unscrunching when the spring's back at original length. I don't want to use the start because some energy was dissipated when this clay block hit this and deformed, right? Some energy went into vibrations and squishing and rearranging the bonds in the clay, right, as it stuck. So you're like, so I can't do that. I'm going to have to start with another point that I know values for, right? But the sad truth is that I don't know any other point, the values for any other point, unless I'm assuming that, again, it hits and these guys have a velocity together before the spring crushes significantly. So I am going to use that value. Okay, that's the value that we calculated back here. That was that VF, all right? That was, I call it VF. It was the velocity right after the collision, okay? Yep. There's right after the clay collides and before it starts crushing the spring. I'm going to go from that point because I know the velocity at that point. Does that make sense? You know, that's where I'm going with. So at that spot, the spring's not crushed, but the clay and the block together are moving. Everything else is at rest. So at that point, so I'm going to do a conservation of energy. Sigma W is delta K, right? And I'm going to say then that the energy, after that hits and it starts crushing the spring, energy goes in the spring, but they're all moving now. They're moving. They're going to kind of do this and wiggle as they slide along because there's no removal stop. And the total energy of the system is constant. We're looking at the point where the spring is at its unstressed length again. So all the energy is in kinetic again. So again, I don't have any outside force on my system, my combined system of clay and block and spring and big block. So there's no outside work. And the change in kinetic is going to be final minus initial. Right, so I can see the kinetic energies are the same because all the energy is in kinetic at those points, and so it's going to be 1/2 mass of the clay plus the mass of the small block plus times that velocity of the clay and the small together squared plus the kinetic energy at the end of the 8 kilogram block, 1/2 mass of the big block times that final velocity of the big block squared. Right, that's my all this is my final kinetic energy because it's of both these things that are moving, minus the initial at the start, just after that clay hits and sticks and this is about to start crushing and pushing on this. It's just them moving. This isn't moving yet. So the initial kinetic energy is just 1/2 the mass of the clay plus the mass of the small block times that velocity. We called that VF before when we solved it. So that's it. That's my equation. Now, you notice they asked, they said, don't bother solving for the velocity, but they want you to write the equations and then show the numerical substitutions. You know why? Because they didn't give you variable names for all this. So when they go to score it, they won't know, like people using come with their own symbols, like I did, MS for small block and B for the big block, right? So they want to see it with the numbers plugged in. So when I write these with the numbers plugged in, I'm going to do that in another color, then this is what they're going to be looking to see. Mass of the clay is 0.1. Its initial velocity, we figured out before that V was 82 meters per second. And on the other side, I'm going to have the clay block and the small block, the clay and the small block. That's a 2.1. Hope that they're okay with me writing it like that combined. The speed of them together, which we solved before, that speed of them together. Oh no, we don't know that one. Right, we don't know that. Yeah. V small, right? Plus the mass of the big block, that is 8 times the velocity of the big block at the end that we're trying to find. This equation is going to be 1/2 mass of the clay plus the small block times the velocity that they're moving at, the small block and that clay are moving at after it's squared, plus 1/2 mass of the big block velocity the big block has afterwards that we're trying to find, minus 1/2 the mass of the clay and the small block together times that VF that we calculated to be 3.9. There. Together, I could substitute and solve, right? I got VS and VB, VS and VB, 2 equations, 2 unknowns. I can see that I've got to the first power into the second power. This is going to be a quadratic. When I substitute in, I'm probably going to end up with a quadratic to have to solve and blah, blah, blah. It's just going to take a lot of time. They're like, let's not waste all that time watching them do algebra. Just set it up. That's fine. Okay, so that's that's the way it looks. All right, let's see what their scoring guide looks like, shall we? For part E. They say, two principles must be applied to calculate the velocity of the 0.8 kilogram block at the instant the spring is no longer compressed: conservation of momentum and conservation of energy. Conservation of momentum, saying that we're going to use conservation of momentum is a point. And you say, yup. Think, think. Okay. MV equals MV plus MV. Hey, that's what we did. Okay. And you see they're calling like V1, V2, V2, V3. They had come with their own variables, right? And of course, they're not matching the way we did it because they didn't tell us what to call them, and so everyone comes with their own names. But just seeing conservation of momentum is enough for a point. Okay, then substituting in your values for that, it would be 2.1 times 3.9. Okay, wait a second. Equals 2.1 times V2 plus 8 times V3, right? Okay, they're calling what I call VS is what they're calling V2. What I call VB, they're calling V3. And then they're looking just after the collision. So they did both of these for just after the collision. But because there's no outside horizontal force acting, it was okay to go all the way to the very start like I did. We're going to get the same answer out. Because if you look at this, again, they're calling what I've got as 0.1 times 82, right? They have, right, and the mass of the clay times the initial velocity of the clay. They're substituting in the combined mass of clay and the small block times 3.9. Well, that is exactly the substitution here. Saying that the mass of the clay is the initial velocity is the mass of the sea. So I mean, that's the same as that. Okay, they went from after the collision. I went from just before the clay hit because I thought it'd be easier to deal with one moving object than two moving objects. Go figure. Anyway, so good enough. So same, it's equivalent. Okay, for indicating that conservation of energy is applicable, we get a point. So I'm giving myself a point for that one too. Yes, we did that conservation of energy here, right? We're getting them that those kinetic energies add to zero before and after. And they're saying, hey, look, we wrote like a term for each of those three objects moving. Good enough. And then they want us to substitute in values, which we did. Half times the 2.1 times that velocity. Let's see here. Again, I'm looking at this. I did look just after the collision here, right, like they did. Oh, I see. They moved it to the same. Okay, I got it. They went ahead and they see. I've got zero equals. They rearranged. They moved this negative term to the other side. Okay, so good enough, right? So this term I have here is what they have on the left side. So 1/2 2.1 times 3.9 squared. Okay, and that's got to be equal to these terms. 1/2 2.1 times VS squared, right, which they're calling V2, plus 1/2 8 times VS. So it's the same thing. Same. Okay, and that's 1, 2, 3, 4 points, right? Oh, look, they say here the equation 3.9 meters per second is V3 minus V2, and two equations one of this equation. Yeah. Okay. All right, so that's it. And if I go run through, you say, hey, does that all add up properly? 3 plus 3 is 6, plus 3 is 9, plus 2 is 11, plus 4 is 15 points. Yep, that's it. Okay, so that is that second free response problem from 1994. All right.